So this is Linear Regression 4, meaning our fourth class, but it's my second video since we went to the online format, and it was supposed to be due on March 31. As it turns out, it's not really done until April 1, so I guess the joke's on me. This is format 228, and it goes with the second half of the StatQuest Linear Models Part 1 video that you watched previously, and that's what my first video was about, and also a very short little video that follows on that one, which is linear regression in R. So you should have already watched the Linear Models 1 in StatQuest, and you should also watch Linear Regression in R StatQuest. The link is on our class homepage. Mathematical model is a mathematical formulation of a real-world phenomena. A regression model explains a response y as a function of one or more explanatory variables, typically denoted with x's. So note that simple linear regression, which is the only thing we've talked about so far, has only one x variable, but our next topic will be multiple regression, and we'll see that in that case that we'll have more than one x variable. So I'm just writing this in the general sense. The general hypothesis test for regression models has a null hypothesis of no linear relationship between y and the x variables. And our mathematical model could just be written y equals beta naught, where the best estimate of beta naught is b0 equals y bar. This is the horizontal line that we've looked at. This is commonly called the reduced model. The alternative hypothesis is that y is a function of a set of x variables. When there is only one x variable, and I'm realizing that I left a word out of the previous sentence, and that word is linear. That function is our equation of a line. This is commonly called the full model. And when I say the full model, I'm talking about this general formulation that could have more than one x variable, not just the simple case with one x variable. To restate those hypotheses, the null hypothesis is the reduced model, and the alternative hypothesis says the full model provides a better fit to the data. For one variable, this is h naught, y equals beta naught, versus ha, y equals the intercept plus beta 1 times x, which is equivalent to a null hypothesis of beta 1 equals 0, the slope equals 0, versus the slope is not 0. Because if the slope was 0, so if this was 0, this term would disappear, and what you would be left with is just y equals the intercept. So these two things, okay, this general way of writing the test is mathematically equivalent to the test that we looked at right before break of testing whether or not the intercept was 0 versus non-zero. And I really do like the approach taken in the StatQuest videos to start looking at the general way of formulating the hypothesis. The test statistic for the reduced model versus the full model.
R squared and for f are the same. That is to say, it's the reduction in variance when we take the weight into account. The denominator is a little different. These dotted lines, the residuals, represent the variation that remains after fitting the line. This is the variation that is not explained by weight. So together, we have the variation in mouse size explained by weight divided by the variation in mouse size not explained by weight. Now let's look at the underlying mathematics. Just as a reminder, here's the equation for r squared. This is the general equation that will tell us if r squared is significant. The meat of these two equations are very similar and rely on the same sums of squares. Like we said before, the numerators are the same. In our mouse size and weight example, the numerator is the variation in mouse size explained sum of squares.
So, and just to refresh our memory, variation around the mean. This is the variation around the horizontal line. Okay, which is always going to be greater than the variation around the regression line. Okay, and it's that same variation around the regression line, that's the unexplained variation that's still remaining in the data after we describe it with our regression model. A lowercase p is used in general to denote the number of parameters in a model. So in y equals just the intercept. So in our intercept only model, we have one parameter, or p for the mean, that's a subscript, using the StatQuest notation. P for the mean equals 1, and over in our equation of a line, we have two parameters, the intercept and the slope, and so P for the fit equals 2, which means in the full model we have P for the fit minus P for the mean additional, so this is the number of additional parameters. And this is the degrees of freedom for the numerator in the F test statistic. So recall that the numerator is the explained variation. So it costs us one additional parameter to explain that variation. The degrees of freedom for the denominator, which is, remember, the variation around the line, is n, the number of observations, minus p fit. So this is something you probably haven't seen before, where we have a test statistic that's a ratio of two variations, and both the numerator and the denominator have degrees of freedom. Okay, so there's the F distribution is used to find the p-value. So here are some pictures of what F distributions look like, taken from Wikipedia. It has a lower bound of 0. Okay, so it's always positive because it's the ratio of two positive numbers. So suppose we have an F test statistic of 2.23. Our p-value is going to be this area under the curve corresponding to the probability of seeing an F greater than 2.23. So again, the p-value is the probability, and F stat will be greater than the one observed if the null hypothesis is true. So remember the central limit theorem from Math 120, which told us if we took many, many samples, like hundreds of thousands, theoretically all possible samples, we took a mean from each sample, then we drew the distribution of those many, many sample means, those sample means would be normally distributed. X bar for sample mean is normally distributed around mu, the true mean. Okay, and then we used that knowledge to find p-values. We said, well, if we observe a sample mean, okay, knowing that those sample means will be normally distributed around the true mean, what's the probability that we would see a sample mean as large or larger than the one that we saw? And this is the same idea that is used to find the p-value for an F distribution. This idea of taking like many samples. And so in the StatQuest video, he talks about this kind of at length, this idea of taking many samples and finding an F for each one. And I think it's a little bit confusing because he doesn't like clearly say in the beginning what he's doing with that. So really he's talking about the central limit theorem argument for how you find p-values. So same idea behind F distribution p-values. So here's the our output, or from the summary of the linear model in the example we looked at earlier. With wind speed, we had 25 observations in this data set. So notice here's the p-value we looked at before break, and that's for the hypothesis the slope equals 0 versus the slope is not equal to 0. And down here is our p-value for our F statistic with the hypothesis of the reduced model versus the full model. And so the thing to notice here is that these two p-values are the same. Okay, so as we talked about on the previous slides, okay, these two tests are mathematically equivalent. So we would expect that they would have the same p-value, and they do. Okay, and the value that we're going to see as we go to multiple regression is that we can use this F statistic when we have more than one X value in our model. So the main ideas from the StatQuest Linear Models 1 video is, first of all, R squared, which is the percent of variation explained by the line or the linear model. Or to be more general, I should say explained by the linear model. In general, we want this to be large, but I have large in quotes here because large is all relative. So in some disciplines, large may be 50% variation explained, while in other disciplines, more like say physics, where we get really good fits, you want to have R squareds in the 90%. So it all depends kind of on the area being studied for like what is large. And secondly, the p-value, which is a measure of how reliable the relationship is. And a small p-value indicates a reliable relationship because that indicates that there's a small probability of seeing an F statistic of that size if there's no true underlying relationship.